So I will be talking also about electrons out of equilibrium, like in the previous talk, although it will be a more focus on real-time dynamics. So I think what we have seen in the previous years are the possibility to have many protocols to control the properties of correlated materials out of equilibrium. I mean, this includes, for instance, the control by very strong electric fields, which can drive electrons over whole portions of the Brillouin zone, or something like Floquet engineering, where like by a time periodic perturbation of the system, you can engineer certain type of Hamiltonians. But there are also other ways by very short excitation of the system, you can generate non-thermal electron population, which eventually change the properties of the system or may even transfer it into a steady or very long-lived phases which do not exist in equilibrium. There's also a certain relation to what we had before with this current-induced non-thermal phenomena. And so for all of these things, what we have to do from a theoretical perspective is that we need to have ways to calculate the electronic structure of correlated electrons under these non-equilibrium conditions. That means either following some ultra-short excitation or in quasi-steady states. And that's what I will try to give you an overview of our attempts to do this in this talk. And as Antoine asked me to have a special focus on non-equilibrium steady states, and thus phenomena, I will also have a more strong focus on this. Okay, so in the first few slides, I want to give a very brief overview of what has to be done or what is done theoretically. So what we aim to study is the typical correlated electron models, such as the Hubbard model, but out of equilibrium, which means we explicitly try to add the electromagnetic field to it, which is typically, for instance, included as a phase factor to the tunneling matrix element, which is called Peierls substitution. And then we want to calculate either the unitary time evolution of this quantum system or also dissipative steady states. For instance, if there are also phonons or other types of dissipation to it, then it will be a long-lived steady state. Okay, so in general, what is the challenge is that if we are dealing with correlated electrons out of equilibrium, we have to take into account that both the spectrum, so the density of states, and also the occupation of states kind of are very strongly linked to each other. And other than in equilibrium, where like the occupation is always fixed more or less or proportional to the spectrum by the Fermi function, they are kind of evolve independently to each other. So I've illustrated this by this very by this sequence of states. So this illustrates the evolution of the density of states and the spectrum in a single band Hubbard model during and after the excitation with a short laser pulse. And you see initially the parameters are here that the system is in a system which has a gap. So the interaction is large enough so to make it Mott insulating or close to the metal insulator transition. And then while the laser pulse is on, that is the second one, there's actually a relatively strong modification of the spectrum itself. So you might notice some narrowing of the peaks and also some transfer of density of states. And then eventually there's a relaxation. And so this is what we need to deal with. So the theoretical framework in which this is done is the Keldysh formalism, in which we deal with Green's function, or like this Keldysh formalism is basically the standard way of doing many-body theory out of equilibrium. So we deal with Green's function in real time, or more precisely on a Keldysh contour, which includes both a real-time portion that's is used to describe the unitary dynamics and also some typical imaginary state, imaginary branch, which is used to prepare the initial state. And then the spectrum and the occupation function are just like Fourier transform or like directly related to this Green's function. And then in terms of this non-equilibrium Green's function, perturbation theory or many-body theory is just analogous to the imaginary time Matsubara formalism. So you have to devise some self-energy, which is either constructed diagrammatically or from approximations such as dynamical mean field theory. You have to solve Dyson equation to sum up the Green's function. So there are, of course, computational challenges which make this different from standard equilibrium theory. And the first is that if your propagators now basically depend on 2 times. You lose time translational invariance, and something like the convolution of the self-energy in the Green's function is no longer calculated in Fourier space, but has to be calculated in real time. And that makes all the solution of these equations some kind of integral equation which can have quite a long memory. So very brief, if you calculate the Green's function, it's a function of 2 time variables, you kind of extend the range in this 2 time plane. But in order to extend it forward in time, as you see in this illustration, what you would have to do is actually integrals over all previous times. And that typically becomes increasingly difficult for longer times. So just the memory or computer memory you need to treat this or to keep this Green's function in time would increase with the simulation time, and quickly, even for perturbative calculation with few orbitals and long time, it can be a limiting. Yeah. So there are some ways to overcome this, but I'm not discussing them in this talk. The other challenge is, of course, that then if you do DMFT, which can be also formulated in equilibrium, in non-equilibrium, you have the mapping of the lattice model to an effective impurity model, and then this effective impurity model is a rather generic Anderson impurity model out of equilibrium, and you need ways to solve this. So there are, I would say, a few numerically unbiased impurity solvers which have been developed or discussed. Matrix product state work for short times, and Monte Carlo methods, such as developed by the chairman, or you have heard yesterday about it by Kai Cohen. And also there are very intriguing ideas. They have 2 posters you might have seen by Olivier Parcouri. So these things have not been used for the long time simulations that I'm presenting here. We still use perturbative methods, namely this non-crossing approximations, but in future, of course, this will be the path to also use this more on perturbative techniques. So I don't want to go more on the theory, and I want to discuss some physics. So this is what you have already seen, the dynamics of the Mott insulator during and after the pulse. So actually the physics which you would see here is a very simple electronic thermalization, in the sense that if you wait long enough, then the occupation function, which is the blue curve here, eventually is just proportional to the spectrum by the Fermi function, that is, the system satisfies this fluctuation dissipation theorem. And this thermalization happens very fast, as you would expect. This is an interacting system where the interaction, the bandwidth, and the final temperature, which is determined by the energy in the system, is of the same order. So there's actually no reason to assume that the time scale would be also anything else than a few inverse hopping. So in a sense, this is a very simple case. But as soon as you go away from this like intermediate coupling regime, then the story becomes different. So for instance, if you are deeper in the Mott insulating phase, you can evaluate the time scale for this relaxation to thermal equilibrium, and you would find that it goes up exponentially just because of the presence of the gap. So this is some older calculation which really shows the time scale for thermalization on a log scale, and around the Mott transition, it is of the order of 1, while if you go in the Mott insulator, where you have a gap, then it becomes a few orders of magnitude larger. And this really means that you can have long-lived non-thermal populations, and this might give rise to new states. So what would you expect in this case is that you have generated population more or less in the upper band. You would expect that there are other degrees of freedom now kicking in, and since the population in this gap state stays more or less trapped in the upper band, there will be processes which relax it within the band. So this is very easy to understand if you have really phonons coupling to it, which is a quasi something like an external heat bath, but also just without phonons at all. In the pure Hubbard model, you would expect that such processes are actually there, because the charge or the charge fluctuations, or if generated, couple strongly to spin fluctuations or also longer range charge fluctuations, which act more or less like a bosonic degrees of freedom, or like a bath to which energy can be transferred. So this physics I don't want to discuss in detail, because this is really the interesting short time dynamics that can be studied, like how on short times energy is transferred from electronic subsystem to other subsystems. But since in this talk I want to focus more on the long time dynamics, I will only briefly discuss one of these two aspects, which is to illustrate this, which is the transfer of energy to these short range spin fluctuations. So the physics is very simple. So if you imagine that you have bioexcitation generated, if you would have an antiferromagnetic spin background and you would generate a hole in there, then it's very well known that, like, if this hole propagates, then it leaves behind a string of defects in this antiferromagnetic background, which actually disturb the antiferromagnetic background and put energy to it. So this process is a very efficient way of dump energy from the electrons somewhere else. And this is not only effective, as you can see in the ordered state as we have here, but you can also see that it would be effective in the disordered state. In order to see this, of course, you have to go a little bit beyond this DMFT approximation and take into account also short range fluctuations, which you can do by cluster extensions of DMFT. So this physics, for instance, you see already if you take the shortest or the simplest cluster approximation, which is a cluster extension with a 2x2 cluster, and then you have within, oh sorry, go back, you have in this 2x2 cluster, you have short range spin correlations. This is the plot on the right hand side, shows the nearest neighbor spin correlations. It's a function of temperature, and then you would see after such an excitation, here there is relaxation within the band. So the plot on the left shows occupation function. The higher energy range is the upper Hubbard band, and you see that the first plot is directly after some excitation, and the second plot is a few inverse hoppings later, and one sees that energy is transferred from the high frequency, high energy part down to the bottom of the upper Hubbard band. And this happens as long as there are short range spin correlations present in the model. This is the second plot, and while this happens, also the spin correlations decay. So in some sense, you can see that the Hubbard model itself provides like a fast and efficient mechanism to dump energy into some other degrees of freedom and provide this internal relaxation. Yeah. So now once we have this internal relaxation, we end up in a state in which we basically have a population in the upper Hubbard band, but it has a more or less cold distribution. And you could ask whether this is actually able to host orders which are not able in equilibrium. Yeah. So another language of calling these states which are kind of becoming quasi-steady because it takes very long for the occupation to relax, but they are not yet completely thermal, is called pre-thermal states. Yeah. So, I'm sorry. So now we would like to address the possibility of these non-thermal orders in these states. However, this is quite difficult or challenging because this needs a very long time dynamics. So there's the idea that possibly if actually this relaxation is prevented by the presence of a gap or some bottleneck, then the state which we generate should be very close to a true non-equilibrium steady state in which it's kept out of equilibrium by a small bias and dissipation. So this idea is actually related a little bit to what probably will be discussed, or a nice idea which will be discussed in the talk later by Zala Lenarchik, although I don't know precisely, of course, what will be in there. But this is the idea that if you have something which is almost conserved, such as the occupation in the upper band here, then you can stabilize a very long-lived state by very weak dissipation. So we are really targeting in this state a state which is time translationally invariant. So mathematically, it has the propagators to depend only on time difference, but the distribution function is not given by the Fermi function. So it's a non-thermal distribution. And this can be targeted directly also in the Geldish formalism and also within a DMFT framework. So what does it mean for this kind of photo-excited state? We would like to have a state which has a population or stable population in the upper band. So the way in which we can establish it is by putting more or less attaching, you can imagine, to each side of your model, you can attach a bath, yeah? Or basically two baths, one which is completely filled by electrons, so electrons can tunnel into the system of interest, and one which is completely empty. But however, the energy range in which these baths exist, in which these baths are, is such that the electrons which enter the site would basically create more W-occupied sites, so would enter the upper Hubbard band, while the holes would create empty sites. So, and in reality, if you would leave the system alone, these holes in W-occupied site would thermalize or recombine, but this is a very slow process. That means you have to attach a bath only very weakly to have a stable state which has a certain population of empty sites and W-occupied sites. And the idea is that this state, which we stabilize as a steady state, is also mimicking the state that would emerge as a quasi-steady state after the photoexcitation, after we wait long enough. So in practice, this is how it would look like. You have the green line is the spectral function of the insulator, and then the blue shaded line is a bath, but actually which has a certain density of states. But since the coupling is very weak, the details actually do not depend really on this bath. Then the red line is the distribution function, which really in this case has generated a population inversion almost. So it has basically filled up the upper band and the lower band is almost empty. Yeah. And now we can, so we have a state, we can also measure the distribution function here. So you would say that it's really the state which is established is one which has more or less a distribution function with a chemical potential and the temperature in the upper and lower band, but a separate chemical potential for the upper and lower band. So this is the state which is established by this procedure. And now we can basically scan the parameters of this bath to generate different steady states. So, and this is what is done in this plot here. So we have the lower line is actually the photo doping density. So the left one would be a completely empty state. The right one would be the limit in which we really have basically only W-occupied sites and holes. So it's the complete population inversion, if you like. And then the dots, the vertical axis is the inverse temperature, and the dots show the states which we realize. And so now the obvious question is, in these states, we can measure the susceptibility towards certain instabilities, such as antiferromagnetism, charge density wave, superconducting, and so on. And in this way, explore this phase diagram of the photodoped system. So what kind of instabilities would you expect? On the left side, of course, where you have only basically almost only singly occupied site in the Mott insulator, this is really the Mott insulator in which you would have antiferromagnetic instability. But the interesting thing, in the same perturbative way, you can also understand the other limit in which you would have only W-occupied and empty sites, so which is basically symmetric. So you can imagine that in this limit, in the strong coupling limit, where the interaction is much larger than the tunneling, you have you can construct on each side a spinor, which is made up of the two relevant states, the W-occupied state and the empty state, and derive a low energy Hamiltonian for that. And the derivation of that is really analogous to the derivation of a spin Hamiltonian for the case where you have only singly occupied sites in the Mott insulator. So you would get a spin model in these spinors which generate this W-occupied empty sites. And the long range order of these spinors is then nothing else than a pair density wave with a staggered phase. And this is called an eta pairing superconductor, which actually has been proposed very long ago, because in the bipartite Hubbard model, this happens to be an exact excited state. So now the question is, of course, in between these limits, and if you go away from this perturbative limit, what kind of states would you have? And it has been proposed by several authors that here, by actually populating these W-occupied states, you can really create this so-called eta pairing superconductivity. For instance, there are a series of nice papers by Kaneko who is now at the Flatiron Institute, who has shown using exact diagonalization calculations that by short pulses in a 1D system, one can enhance these eta pairing correlations. And also there are the nice proposal that by continuously driving the system, you can overpopulate these doubly occupied states, and in this case, sorry, in this case, generate this eta pairing. Now we can do what I said before, along the lines or scans to the phase diagram, measure the susceptibility, and you really see you have a so large range in which this susceptibility shoots up by orders of magnitude, which we can interpret as the region of stability of this eta pairing state.
Martin?
So this is it's 5 minutes or?
Yeah.
Okay, yeah. This is this is what I wanted to say about this long-lived state, which are basically prepared as a non-equilibrium steady state. Now, since also this is a session about real steady states and current-driven states, I wanted to, in the second part, really add one example or show you briefly one nice example, which is a real current-driven steady state. So for this, I would completely switch here the setting. So it's again the Hubbard model, but this case it's actually an attractive Hubbard model, which wouldn't actually be matter a lot. So in the attractive Hubbard model, at least the weak coupling, you would expect an instability to a charge density wave state, which has a typical mean field behavior where the order parameter decreases as a function of temperature. So now is the question, what happens actually to this phase if we drive a current through it and discuss a real non-equilibrium steady state? Yeah? So because this is, in terms of methodology, very similar to what I have done in the previous talk. So what we really do here is we attach a heat bath to it, which is the dissipation term, which mimics the phonons in the material, and apply a bias to the material, which then leads to a steady state current. And we measure the order parameter. So what you see on the left side is really the current as a function of the voltage as we increase the voltage. And for very small voltages, you see there is no current. This is clear because we are in an ordered phase, which is an insulator. But then the current goes up and eventually jumps on another branch, which more or less, if you would extrapolate it to zero, is one which has a linear current voltage characteristic. So this is the metal. Yeah. So, but you immediately see that in contrast to the on the right hand side, you see in these two branches the order parameter, which also, as I said, is disordered, and then it basically jumps to the ordered phase. What you immediately notice that in contrast to the equilibrium state is actually the current-driven transition becomes a first-order transition, and basically the mechanism seems to be that driving the current through it makes the charge density wave eventually unstable. So the immediate question is whether this is more or less a thermal mechanism. So to do this, we can evaluate directly the distribution functions in this current-driven state. And this is done here for 3 different points. Point 1 is basically in the charge ordered phase. There is point 2 and 3 are in this metallic state. And for all 3, the distribution function more or less looks nicely thermal. So we can make a fit with the Fermi distribution function to it and then measure the temperature. So then we have, when we can compare this order parameter, which we have in the steady state, plot this as a function of the effective temperature in this steady state. And this is the upper blue curve, which you see here. So the green curve is the order parameter as a function of temperature in equilibrium. The order parameter is a function of the effective temperature in the current-driven state. You see is actually reduced. So in contrast, so it's not just the thermal mechanism, but it's really the current, in addition to the thermal mechanism, suppresses here the order parameter even further. You can get the same effect by looking also at susceptibilities, which I don't want to show here. So if you put this all in a small phase diagram, you have as a function of the interaction U and the voltage, the color codes somehow the effective temperature in a metallic state. And you really have a whole region of states here in which the metal is in which the metallic state or the disordered state is actually stabilized with respect to the charge density wave, although the effective temperature is below the transition temperature. So this is really a mechanism in which we have a non-thermal control of some phases. Now, the subsequent question would be whether in this regime, if, for example, you have a phase which is competing with the charge density wave phase, this suppression of the charge density wave phase could help other phases to emerge. So this is already the end. It was quite like many topics. I discussed kind of more or less electrons out of equilibrium. The first one was the possibility to go from a photoexcitation to a steady state, which is more or less very reminiscent of a non-equilibrium steady state and can have different orders. And the second one was, this is what I showed here. And of course, the obvious question is whether this can be extended to more interesting systems, and also whether this would be possibly ideal to use more unbiased impurity solvers, which can target this non-equilibrium steady state. And the second part was a non-thermal stabilization of a real steady state. And of course, the most important thing is the acknowledgements. So a lot of this work was done with Philip Werner, who had already escaped the same route that I'm taking tomorrow via Istanbul. And then, of course, there's a lot of work done by Dennis Golesh on this non-equilibrium DMFT. The non-equilibrium steady state was done by Chai-Chun Lee, who's a postdoc in Erlangen, and he's really done a great work, not only in this respect, but also in other topics. And the last one was done for the master project of Anne Matisse, who is now doing her PhD in Cologne. So with this, I thank you for your attention and open for questions.
Thanks, Martin. So for the first question, we're going to go directly over to Antoine, who should be enabled as a panelist.
Yes, can you guys hear me?
I can hear you.
Okay, wonderful. So very nice talk, Martin. I have a question about the very last part. And perhaps this is because I was not listening carefully enough, but can you re-explain how you can assess that this current stabilized state is actually super cool? So in other words, how can you show that it is stabilized at a temperature which is, you know, it is not just heating?
Yeah, I think I was probably a bit fast on this part. So we really measure the distribution function in this state. Yeah, and of course it's not perfectly a thermal distribution. So this would be the left plot here. So for each state, we can measure the distribution function and compare it to a Fermi Dirac distribution function. And it's not perfect, of course. It has slight steps here, which are related to the voltage. But if we take this as a, if we approximate this by a thermal distribution function, we get the effective temperature of that state. Yeah,
I see.
And then we look actually whether at this effective temperature. So, for example, if you look now in this plot, we look how, like the upper states here are the metallic states. So I would point on it, but I can point. So the states in above the effective temperature of here 0.1 are states in which we have stabilized the metallic state, although the effective temperature is below the nail temperature or the ordering temperature.
Okay, thank you.
So really, we look at the we basically measure the temperature of the current-driven state from the fluctuation dissipation theorem and compare that temperature to the ordering temperature, and it's below. So.
Okay, thanks. Next up, Andy.
Hi. So actually, I wanted to pursue this same point, looking at the linear instability of the metallic state, right? Which you argue is super cool because the effective temperature is less. But this is a metallic state with no gap or anything. Yes. Therefore, there's something else about the state in the presence of the current, which is different from a conventional metallic state.
Yes.
Can you say what that difference actually is?
Well, like if you just
you said there were very subtle differences in the Fermi function, but this is a big effect. There must be something more.
Yeah, so I would say probably in the Fermi function alone, it's very hard to see. I would rather wonder like why actually the ordered state cannot basically survive in the presence of a current like this. Like you have the current going through the ordered state would generate the Fermi Dirac like distribution function, but the order is suppressed beyond that. So for example, if you look in the ordered state here, for smaller effective temperatures, you really see that the order is suppressed beyond just what you would expect from the effective temperature.
Right.
So this
no,
is
no, but my question was the linear instability of the metallic or disordered state. Yeah. What you say is that the metallic state remains linearly stable down to an effective temperature which is lower than the equilibrium CDW temperature. So the question is, what is it about that state which is keeping it linearly stable?
Well, that is hard to say because it must be somehow related in this or hidden in these subtle differences to the Fermi-Dirac distribution. Fermi-Dirac distribution probably doesn't show it nicely. So that's true. I don't have a good intuition for that. For the ordered state, it's for me much easier to say. It's like if you have a crystal and you try to drive a current through it, that destabilizes this crystal beyond just thermal effects.
Yes. So may I ask? This is just to make two quick suggestions, and then I'll shut up. I promise, more or less. In terms of the linear instability of the metallic state, are you dealing with a cubic or hypercubic lattice? And how big is the current? I mean, have you pushed because the current shifts the Fermi function, if I just think in terms of a non-interacting picture, and is it big enough to shift you somewhat away from a density of states peak, for example?
Oh, actually, this is more or less a beta lattice calculation.
Beta lattice, so there's no particular
that means
structure.
the density of states is more or less flat at the Fermi edge.
Right, so it's not bad. But how big is the current in here? The
current is okay. So I don't have numbers, but
well, what's the fractional shift in the Fermi in the KF? That's a good measure.
So if you see, you could look at the steps. Yeah. So how wide are the steps or these little steps on the Fermi function, which you see here, and they are of the order of the voltage here is of the order of 0.05. Yeah, which is much smaller than the bandwidth. It's still very large compared to typical experiment. So this is a purely electronic effect. And so the voltage is, of course, immense, if you like, but it's still much smaller than the Fermi edge.
I see. Right. That's very, very interesting. Thank you very much.
I'm sorry for a probably very simple question. I just want to know how you dissipate the energy that you put in. Do you have some leads or, how do you do that?
That's a good question. In this case, we have just added an electron-phonon self-energy diagram with some broad spectrum of the phonons. Okay. So it's like a DMFT plus this electron-phonon self-energy diagram.
Which is sort of not self-consistently.
But the phonons are not updated self-consistently. In that sense, they only act as a dissipation. But like in the self-energy diagram, you have electron propagator, so it's basically lowest order self-energy diagram. You have electron propagator, which is updated self-consistently, but phonon propagator, which is not updated self-consistently. And that means there's no feedback on the phonons. Phonons are always kept in equilibrium, and that makes it act as a dissipation.
Okay, thank you very much.
You maybe kind of already answered the question, but so can you give a bit more intuition how the current is destabilizing the charge density wave or stabilizing the metallic state? So what's the intuition for this effect?
Well, there I have to say that probably I don't have a good intuition to me. For me, I only have this like simple picture, which is like what I said. Like if you have a crystal, you try to drive a current through it, you actually destabilize it. It's like a little bit like you could probably also ask the classical question whether you have a block of ice or you want to freeze water, but you want to freeze water in the presence of a flowing current. Actually, does that lower the freezing temperature if you have a very high current? So, and that is the effect, what is seen here, the classical analogy. I must say that probably I cannot put a very nice physical intuition at the moment. Yeah. So.
Okay. All right. Thank you very much. I see we have no more questions from outside of the lecture hall here. Is there anything in here? Because if not, we're going to go to our coffee break outside and we'll reconvene in half an hour.
Okay.
But before that, let's thank Martin again.
Thank you.